Hello everyone. In this video, we are going to discuss about shapes of atomic orbitals from the chapter 2 structure of atom class 11 chemistry. You see, what is an orbital? An orbital is the space around the nucleus in which the chance of an electron occurring is at its highest level. That is, it is the most probable area of finding the maximum density of electrons in an atom. You see, S subshell has only one orbital, P subshell has 3 orbitals, and D has 5 orbitals, F has 7 orbitals. You see, S orbital, we will be discussing about the shapes of S orbital, P orbital and D orbital in this video. So you see, S subshell has only one orbital, and that orbital, that is S orbital, it is spherical in shape. S orbital is in spherical shape and it is non-directional. That is, all the s orbitals means 1s, 2s, 3s, etc. They are spherically symmetric and the probability of finding the electron at a given distance is equal in all directions. That is, you see, consider this as the s orbital, it is spherical in shape. Here I have taken the three axes x, y and z. I have chosen a point P1 which is r distance away from the center, and P2 r distance away from the center, as well as P3 r distance away from the center. Okay, so you see, all these points P1 and P2 are at the same distance from the center. Then the probability of finding the electron at P1, that is equal to the probability of finding the electron at P2, and that is equal to the probability of finding the electron at P3. That is, the probability of finding the electron at a given distance r, it is equal in all directions. Okay, the probability of finding an electron at P1, P2 and P3 are the same. That is, the probabilities is equal in all directions along the x direction, y direction and z direction. Now, let us talk about the boundary surface diagrams of s orbital. See, boundary surface diagrams, they are graphical representations of the surface that encloses a molecule or an ion, indicating the boundary beyond which electrons are not likely to be found. See, boundary surface diagrams help visualize the distribution of electrons in orbitals and how they occupy in space around the nucleus. See, boundary surface diagram for a s orbital, it is actually a sphere centered on the nucleus. The boundary surface diagrams for 1s orbital and 2s orbitals, they are spherical in shape as shown in these two figures. See, for 1s orbital, the boundary surface diagram is a single continuous sphere. For 2s orbital, the boundary surface diagram is like two concentric spheres with a nodal space in between, these two concentric spheres. That is, you see, both 1s and 2s orbitals boundary surface diagrams are spherical, but 2s orbital is larger than 1s orbital. You see, the probability density of an electron, it is also known as electron density. It is a measure of the likelihood of finding an electron within a given region of space. So, the region where this probability density function reduces to 0, that region is actually called as nodal surfaces or simply nodes. So, you see, node is a point in space where the probability density of finding an electron is 0 or electron is unlikely to be found here. Okay, so you see, these shaded yellow regions represents most probable regions of electrons. So, the probability density of electron is high in this region as well as in this region. That is, there is a chance for finding an electron here as well as in this region. Okay, similarly for 1s orbital, everywhere it is the same. Now you see, the 2s orbital has two most probable regions while 1s orbital has only one. So in general, you see, it has been found that ns orbital has n minus 1 nodes. See, in general, ns orbital has n minus 1 nodes. What is this n? N is the principal quantum number which we have already discussed in our previous video. See, as the principal quantum number n increases, the number of nodes also increases. For example, if we consider 1s orbital, it has no nodes because ns orbital has n minus 1 nodes. So if we consider 1s orbital, n value is 1. So number of nodes which is n minus 1, that is 1 minus 1, which is equal to 0. So 1s orbital, it has no nodes. Okay, then what about 2s orbital? N value is 2. So number of nodes will be n minus 1, that is 2 minus 1, which is 1 node. So 2s orbital has 1 node as we have seen in our previous picture. Then if you consider 3s orbital, n value is 3. So number of nodes is n minus 1, which is 3 minus 1, that is 2 nodes. Okay, so you see, if we consider 1s orbital, it has no nodes. If we consider 2s orbital, it has 1 node. For 3s orbital, it has 2 nodes. That is, as the principal quantum number n increases from 1, 2, 3, etc., the number of nodes also increases 0, 1, 2, etc. Okay. So you see, we said 1s orbital has no nodes. So you see, everywhere the same probability to find the electron. Okay, 2s orbital has 1 node. That means you see, there are 2 shaded regions here which actually represent the most probable regions of electrons. So there is a chance of finding an electron here. There is a chance of finding an electron here as well. But in between these two, there is a space which is marked as node. That is, the probability of finding an electron in this region is 0. So 2s orbital has 1 node. Similarly, if you consider 3s orbital, it will be having 2 nodes. Okay. Now you see, the probability density can be visualized in terms of charge cloud diagrams. See, in these diagrams, the density of the dots. Okay, we will use the dots to represent the density of, the probability to find an electron. So, in these charge cloud diagrams, the density of the dots in a region that represents electron probability density in that region. So you see, this is the charge cloud diagrams for 1s orbital. This is the charge cloud diagrams for 2s orbital. So you see, here we have so many dots together and there is a gap between this outer one and this inner one. And this outer one also, there are so many dots present here. That means there is a probability of electron to find an electron here, and there is another probability of finding an electron here. But in between, there is a space which is actually called as node. That is, the probability of finding an electron in this space is 0. Okay. You see, the size of the s orbital increases with increase in the principal quantum number n. That is, if you consider the size of the 4s orbital, it will be greater than that of the size of the 3s orbital. That will be greater than that of the size of the 2s orbital, and it will be greater than that of the size of the 1s orbital. Because you see, when we consider 4s orbital, its principal quantum number n value is 4. For 3s orbital, it is 3. For 2s orbital, it is 2. For 1s orbital, it is 1. So the size of the s orbital increases with increase in n. For 1s, this will be the, if we consider this as the size of the 1s orbital, then for 2s, its size will be greater than this. For 3s, it will be like this. 4s, it will be like this. Okay, so the size of the s orbital increases with the increase in the principal quantum number n value. And the electron is located further away from the nucleus. As you see, the orbital wave function psi for an electron in an atom has no physical meaning actually. It is simply a mathematical function. The psi, which is the orbital wave function, this is simply a mathematical function of the coordinates of the electron. However, for different orbitals, the plots of the corresponding wave functions psi as a function of r is the distance from the nucleus, they are different. That is, you see, this is a plot of psi versus r, and this is also a plot of psi versus r. This is for the 1s orbital, this is for the 2s orbital. Okay, so for 1s orbital, principal quantum number n is 1. For s orbital, we know that azimuthal quantum number L is equal to 0. Similarly, for 2s orbital, n value is 2. This is s orbital now. So, azimuthal quantum number L is equal to 0. So, you see the plot of the wave functions as a function of r for 1s orbital and 2s orbital, it has different nature. It is not the same. They are different. Okay. Now, you see, according to Max Born, a German physicist, the square of the wave function, that is psi square, the square of the wave function at a point gives the probability density of the electron at that point. The square of the wave function psi square at a point, it gives the probability density of the electron at that point. You see, the variation of psi square as a function of r in nanometer for 1s and 2s orbitals are given here. You see, the wave functions for 1s and 2s orbitals are different. You see, for 1s orbital, the probability density is maximum at the nucleus and it decreases sharply, to 0, as we move away from it. That is, for 1s orbital, the probability density of maximum, it is actually maximum at the nucleus and it decreases sharply as we move away from it. That is, as r increases. For 2s orbital, the probability density first decreases. First it decreases sharply to 0. Then again it starts increasing. After reaching a small maxima, it decreases again and approaches 0 as the value of r increases further. So, the region where this probability function reduces to 0, that is actually called as nodal surfaces or nodes. Now, let us consider the p subshell. So far, we have been discussing about the f subshell. Now, let us consider the p subshell. See, p subshell has 3 orbitals. The boundary surface diagrams for 2p orbitals. 2p orbitals. For p orbital, L value, azimuthal quantum number L value is equal to 1. That is actually shown here. See, we have 3 2p orbitals. So they are named as 2px, 2py and 2pz. Please note that this is for 2px, this is for 2py and this is for 2pz. The order is different. So you see, the boundary surface diagrams for p orbital. See, for 2px orbital it is like this, for 2pz orbital it is like this, for 2py orbitals it is like this. Anyway, when you see the boundary surface diagrams for all the 3 2p orbitals, it actually consists of 2 sections. Like one section here, this is one section and this is another section. All the 3 2p orbitals consist of 2 sections. They are actually called as lobes. So you see the boundary surface diagrams for p orbitals consist of 2 sections which are called as lobes. See, the probability density function is 0 on the plane where these 2 lobes touch each other. That is, the point where the 2 lobes touch each other, that is a node where the electron cannot be located. All the p subshells have dumbbell shapes. You see, each p orbital has same size. Same size and energy. But each p orbital is oriented along different axes in space. That is, the way the lobes are oriented, it is different for all the 3. Since the lobes are considered to be along the x-axis, this one is along the z-axis, this one is along the y-axis. Since the lobes are considered to be along the x, y and z axis, they are given the designations 2px, 2py and 2pz. You see, for 2p orbitals, principal quantum number n is equal to 2. For p orbitals, azimuthal quantum number L is equal to 1. So you see, what about the ml value? ml value means magnetic orbital quantum number ml. That will be from minus L to plus L. So here L is 1. So minus 1 to plus 1, that is minus 1, 0, plus 1. Okay, so you see there are 3 possible values of ml. So there are 3 orbitals whose axes are perpendicular to each other. Okay, now you see p orbitals increase in size and energy with increase in the principal quantum number n. That is, the size of p orbitals and the energy of p orbitals that increase with the principal quantum number. The order of size and energy of the various p orbitals is given here. 4p for 4p it is greater than that of 3p, which is greater than that of 2p. That is, the size and energy of 4p orbital will be greater than that of 3p orbitals, which will be greater than that of 2p orbitals. Because you see, for 4p the principal quantum number is 4. So with the increase in the principal quantum number, size and energy also increases. For 3p it is 3. So it will have less energy and size that of 4p, like that. Okay, you see, for p orbitals, the number of nodes is given by n minus 2. Okay, so for p orbitals, the number of nodes can be calculated by using this equation n minus 2. Okay, that is, for 3p orbital, the number of radial node will be equal to n minus 2, that is 3 minus 2. 3 minus 2 is actually what? 1. Okay, if you consider 4p orbital, the number of radial node, what do you mean by radial node? There are 2 different nodes that we will be discussing in the same video itself. Radial node or nodal regions are the spherical surfaces around the nucleus where the probability of finding an electron is 0. Okay, and we will be discussing out angular node as well in the same video itself. Angular nodes are actually the nodal planes. So this is actually the equation for the radial node, which is actually n minus 2. So for 4p orbital, the number of radial nodes will be equal to n minus 2, that is 4 minus 2, because n is 4. 4 minus 2 is 2, and so on. Okay. Now you see, for L equal to 2, the orbital is known as d orbital. That is, L is equal to 0. What is L? Azimuthal quantum number, which we have already discussed in our previous video. L is equal to 0 for s orbital. L is equal to 1 for p orbital. L is equal to 2 for d orbital. So for L equal to 2, the orbital is known as d orbital. So now let us discuss about the d orbitals. See, the minimum value of the principal quantum number n is 1 for s orbital. Okay, and 2 for p orbital. That is, s orbital starts from 1. 1s, 2s, 3s, like that. The minimum value of principal quantum number is 2 for p orbital. So p orbital starts from 2p, 3p, 4p, etc. Okay, similarly, the minimum value of the principal quantum number n is 3 for the d orbital. That is, we don't have 1d or 2d orbitals. It starts from 3, that is, we will have 3d, 4d, 5d, etc. orbitals. Okay, so you see, L equal to 2 for d orbitals. So what about their ml values? Azimuthal quantum number ml? Azimuthal quantum number ml is actually from minus L to plus L. So minus 2 to plus 2. That is, the values are minus 2, minus 1, 0, plus 1, plus 2. So there are 5 ml values. So there are 5 d orbitals. Okay. You see, the boundary surface diagram of d orbitals are actually shown here. See, this one is for dxy, this one is for dxz, dyz, dx square, y square, dz square. So you see, the 5d orbitals are designated as dxy, dxz, dyz, dx square, y square, dz square. See, the shapes of the first 4 d orbitals are similar. Okay, the shapes of these 4 d orbitals are similar. But the 5th one, that is dz square, its shape is different from others. Okay, you see, all the 5 these are actually the 3D orbitals. Okay, these are actually the 3D orbitals. So you see all the 5 3D orbitals are equivalent in energy. That is, they have the same energy. Okay, now you see the d orbitals for which the principal quantum number n is greater than 3. Okay, the d orbitals for which the principal quantum number n is greater than 3. That is 4d, 5d, 6d, etc. They also have shapes similar to the 3D orbital, but their size and energy are different. Okay, that is the shapes of 4D orbitals, 5D orbitals, 6D orbitals. They are similar to the shapes of 3D orbitals as shown here, but their size and energy are different. Now, let us discuss about the two types of nodes. The two types of nodes are radial nodes and angular nodes. Angular nodes are also called as nodal planes. You see, radial nodes, which are also called as nodal regions. Okay, angular nodes are also called as nodal planes. Radial nodes are also known as nodal regions. So, radial nodes, these are the spherical surfaces around the nucleus where the probability of finding an electron is 0. And you see, the number of radial nodes increases as the principal quantum number n increases. Okay, angular nodes, they are also known as nodal planes. It actually passes through the nucleus, that is through the origin. Okay, you see, the number of angular nodes is usually equal to the azimuthal quantum number L. The number of angular nodes, that is actually equal to the azimuthal quantum number L. You see, angular nodes are actually known as nodal planes that passes through the nucleus or the origin. Okay, if you consider the NP orbital as well as ND orbitals. For NP orbitals, n value can be 2, 3, 4, 5, etc. because the minimum value of principal quantum number for p orbital is 2. For ND orbital, n value can have 3, 4, 5, etc. because the minimum value of principal quantum number is 3 for d orbital. So 2 cannot be or 1 cannot be possible here. Okay, so for NP and ND orbitals, the probability function, that is, in the case of PZ orbital, the xy plane is a nodal plane. That is, in that plane, we cannot find an electron. The probability of finding an electron is almost 0 in that plane. Okay, so in the case of PZ orbital, xy plane is a nodal plane. That is, the probability of finding an electron in the PZ orbital is 0 at the xy plane. And for dxy orbital, there are two nodal planes or there are two angular nodes. See, the number of angular nodes is given by the azimuthal quantum number L. Okay, so for p orbital, the number of angular nodes will be equal to 1 because for p orbital L value is 1. For d orbitals, the number of angular nodes will be equal to 2 because for d orbital, the azimuthal quantum number L is equal to 2. Okay, you see, if you consider the total number of nodes means the sum of angular nodes and the radial nodes. So, the total number of nodes, that is actually equal to n minus 1, where n is the principal quantum number. Okay. So, in this video, we have discussed about the shapes of atomic orbitals. Specifically, we have discussed about the s orbital, p orbital and d orbital. I hope it is clear to you. Thank you.